Hi, everyone. Welcome back to the Lloyd's Academy Asia Pacific, Middle East, and Africa Educational Program 2024. My name is Shai from the Market Development Team for Lloyd's Asia, our platform in Singapore. It has been an incredible learning journey over the past 2 months, and today we have come to the final session with a very interesting topic on the construction of offshore wind farm presented by Sedwick. Thank you all for joining us today. For those who might have missed this, the session will be recorded and made available online in Lloyd's of London official YouTube channel under Market Voices APMEA Educational Program 2024. For now, feel free to ask any questions that you may have and share your thoughts as well as we go along the presentation. Please do remain until the end of the presentation to fill in the feedback form and claim your certificate of attendance. Just a disclaimer, the views and opinions expressed in this webinar are those of the speakers and do not necessarily reflect the official policy or position of Lloyd's. The information provided is for general informational purposes only and should not be construed as professional advice. Introducing our esteemed speakers for today, we have the CEO and Head of Major Complex Laws in Sedgwick, Nigel Cook. Nigel brings a wealth of specialist industry knowledge and experience to Sedgwick. He began his adjusting career and gained his chartered status in 2004 in New Zealand before relocating to Abu Dhabi and to Singapore. He specializes in handling large and complex losses relating to material damage, engineering, onshore and offshore natural resources, petrochemical, marine hull and machinery, warranty, liability, as well as associated claims for advanced loss of profit. Meanwhile, Neil Best is the Director of Energy in Sedgwick, Asia. Neil is a specialist offshore loss adjuster with extensive experience managing operational losses to floating production, storage, and offloading vessels and their related subsea architecture. He also has a significant experience with marine in-water seismic equipment losses and has managed various claims in the renewable energy sector, including onshore solar farms and nearshore wind turbine generators. And lastly, we have Liu Buntat, who serves as an executive energy adjuster in Sedgwick, Asia. He is a seasoned loss adjuster with extensive experience in handling a diverse range of claims, including property damage, machinery breakdowns, alternative energy, mining, marine incidents, among many others. Liu's expertise covers various aspects of insurance assessment and evaluation. Without further ado, I am handing over the time now to Nigel to do an introduction. Thank you. Nigel?
Thanks, Shay. I'd like to thank Lloyd's Academy for providing us with this opportunity to present on the construction of offshore wind farms. Today, we'll give a brief overview of the construction technology, some of the terminology, and some typical claims that we are likely to see in offshore wind farms. Next slide, please. I'll just run through these quickly because they're just a background to Sedgwick. For those of you who don't know who we are the world's largest insurance service provider, and we specialize in both traditional loss adjusting and bespoke solutions for insurers in order to get claims settled. Next slide, please. We're a fairly large organization. As you can see, we've got 33,000 colleagues across the globe. This number is always changing. It's always going up. We're based in 80 countries. We have 125 distinct types of claim solutions that we deal with. On average, it's about 10.1 million claims a year. We generally have the average client partnership generally results to or relates to TPA, and we have a 98% retention rate. Next slide, please. This is just a general overview of where we are in the globe. The dark blue areas are where we have direct offices. Light blue is affiliate offices. And the grey areas, we don't have an office, but coverage is available through a wider network. This is a snapshot of us in Asia. We have 600 plus colleagues. So again, we are the largest loss adjusting company in Asia. We're based in 9 countries with 42 offices, and we deal with about 42,000 claims a year. Next slide, please. So as part of our growth and diversification strategy, we're currently building a natural resources team, which will be hubbed out of Singapore. We're also currently in discussions with specialist adjusters in several other countries in Asia, Thailand and Indonesia, to name just 2. So at the moment, the energy team consists of myself, Neil Best, and Lou. We are generally offshore marine construction adjusters. So we do a lot of work and bespoke construction policies such as Wellcar, but we also deal with operational losses. I was working out just before we started the presentation how many years experience we have between us, and we have well over half a century of experience, which makes me feel quite old, to be honest with you. So with that, if we can go to the next slide, please. So today we'll just have a quick look at an offshore wind farm. We'll have a look at some of the typical offshore vessels, the construction vessels. We look at some case studies and some of the challenges associated with handling those losses, and then we'll open it up for a Q&A session. And with that, I'll hand it over to Neil.
Okay, many thanks for the introduction, Nigel. I've been told I've got quite a strong accent, so I'm going to try and slow down, but understand the presentation, the webinar is being transcripted. So those who are interested that don't understand can maybe read back. So over the next sort of 15 to 20 minutes, I'm going to start with a high-level summary of the offshore wind farm construction and installation, as well as talk about vessels used and the component parts to the wind turbine generators. And again, apologies for stating the obvious. Offshore wind farms is just that, wind farms located in the marine environment offshore. There are significant benefits, as you can see, to offshore wind. You can achieve higher wind speeds, generate more electricity, and have less of an impact on people and the environment. Like most things in life, though, there are aspects that are not so positive. Construction and installation offshore is expensive and complex, and when things go wrong, repair and rectification is troublesome, to say the least. So ideally, you locate your wind farm in an area with the highest possible consistent wind. But again, this leaves you potentially exposed to storms, hurricanes, earthquakes, and typhoons. Additionally, there could be environmental impact to marine life, its ecosystem, and if your wind farm is near shore, it may be considered unsightly by locals and tourists. So as you can see from the slide, Asia has taken over the world as the largest regional offshore wind market, and it's likely to maintain this in future projects, which are due to commence this year and in 2025, which is set to be some of the biggest. Next, please. Okay, just a brief comparison of some of the largest wind farms in Europe with those in Asia. Some of the large currently operating wind farms are off the coast of the UK, the Hornsea 1 and Hornsea 2 project. And there's also the Hornsea Project 3, which has commenced in part with vessels being mobilized to start installing the protective sleeves for the offshore cables. The most notable wind farm in Asia is in Taiwan. Lloyd will be able to help me with the pronunciation of this, in the Changzhou region wind farm. The capacity there will be over 43,000 megawatts per year. Okay, next slide, please, Lou. Let's go through the main components of the wind farm, starting on the left with the wind turbine generator. At the base, in this example, you can see Lou's just hovering over. That's the monopile foundation. This is piled into the seabed using a hydraulic hammer on the offshore construction vessel. The yellow piece is lifted from the vessel and grouted. This is the transition piece, and it's secured. And the long white mast structure. Okay. Then we have the working parts of the wind turbine, or installed the nacelle atop of the mast, and the blades are then installed. We need to talk about some cabling. So going back to the base of the wind turbine, the inter-array cable, which is that long yellow line that Lou's highlighting, is installed from each wind turbine to the next. And if you look at the diagram on the right, it's a very simplistic look of a string of wind turbines. So you can see one goes from one to the next to the other in the series. So after they connect to each other, they go to the offshore substation platform, where they are where the electricity is converted, and then it goes to the export cable to the onshore substation, and then finally to the grid. Okay, yeah. So just thinking about the what we said about Taiwan. This is just a few salient details of this project. As you can see, it's located just less than 45 meters of water, and each turbine has a 8 megawatt. It's in technically shallow water, and the turbines in this case are installed with pile jackets. But we'll discuss the different fixed methods for installation in the next slide. Two locations, 2B and 4 regions of the wind farm are due to be operational in 2025 and fully commissioned by 2026, making this one of the largest in the world. Okay, we saw earlier that in the typical field layout slide, that a monopile was used as the foundation for the wind turbine generator. However, as you can see, there's various other options worth mentioning. From left to right, we have the gravity base, typically in shallow water, sort of 12 to 15 meters. Quite a large footprint, and uses concrete and steel bases to support. This is technology borrowed from oil and gas from the 80s. Then we go to the suction bucket monopile, just to the right of that. Cylindrical structures made of steel or concrete, which create a pressure difference between the inside of the bucket and the surrounding water. This allows the bucket to be sucked to the seabed, thus securing it. We've already discussed before in the typical layout, but this is the monopile foundation. It's the most common, and it works very, very well in sandy and gravel seabed conditions. Simple and efficient to install. We're gradually getting deeper and designed for up to sort of 50 meters of water. You have the tripod. It's a cylindrical central column connected with 3 legs, and it's piled to the seabed, so it's hammered in. But we'll talk about that. And then to the right, the last one is the jacket foundation, usually installed with piles or suction caissons into stiff clay or medium to dense sand. Okay, next please, Lou. Okay, so after sort of 50, say 60 meters of water, the wind turbines tend to be floating. The image on the left shows sort of semi-sub structure. So these are fabricated and assembled on shore before being floated out to sea and then hooked up to the mooring system. So the mooring chains are the white lines on the diagram, and they're connect to the wind turbine and then get secured to the piles on the seabed. If you look at the black line, which is the inter-array cable, so it's the part of the transmission of the electricity, and the yellow parts there are the buoyancy aids, which help reduce the tension on the cable, managing the sort of dynamic nature of the loads. There's a few other designs. And there's about 450, but the sort of main types are semi-sub, but we'll talk about some of the other ones. There's a barge, which not dissimilar to a vessel, is a hull structure, large surface area, in contact with the water, anchored to the seabed with a similar type spread marine system as the semi-sub. Spar is like the monopile, only floating cylindrical structure, ballasted at the bottom. And again, this anchored to the seabed. And then a tension leg platform, structure that's anchored to the seabed, but the mooring system goes straight down, not in a catenary to the seabed. Okay, next slide, please, Lou. Okay, the image on the left, I think everybody would recognize that, is the complete wind turbine generator. And the yellow part just shows the transition piece. You see on the middle picture being installed on the monopile. The blade radius depends on the wind turbine size, and nowadays these are becoming massive, in excess of 120 meters in diameter. In radius, and they're just going to get bigger. So the image on the far right shows the photo inside the wind turbine mast. So it's hollow, so tubular. It's got a ladder, as you can see, for maintenance, and this where it contains the power cables of the equipment, the switchgear, the inverter, the transformer. Okay, next slide, please, Lou. So at the sort of business end of the wind turbine generator now, that's the nacelle on the left is a cut-through diagram, which sits atop of the mast. So hopefully you can see the wind rotates the blades, which are connected to the drive shaft via gearbox to the generator, and simply producing electricity. And as we saw earlier, the blades are enormous, and hopefully you can tell from the images on the screen. You can pick out some people, like at the bottom there, and obviously the nacelle as well. So a 14 megawatt capacity wind turbine can cost around sort of 14 million US dollars and weigh between 400 to 700 tons, including the hub. So pretty big. Okay, next slide, please, Lee. Okay, let's talk about how the electricity produced finds its way to your home. So we discussed before the blades of the wind turbine spin, causing the generators to produce electricity. Typically, this is 600 volt DC, which is then inverted and transformed into either 33 or 66 kilovolts, which goes through some switchgear on the turbine, then out the inter-array cable at the foundation to the offshore substation platform. So the inter-array cable, which is the green line you can see that's connecting at the base of the wind turbines, is typically composed, and just have a look at the cut through underneath, a 3-phase copper cores with fiber optics included, and for data and temperature measurement. So the cable is armored, insulated, and it's sheathed in a cross-linked polyethylene with an outer serving. And it connects one to the next, and then the blue line, it goes, the green line, it goes to the substation, and the export cable is much the same. It's just, you can see there, it's just heavier, and the typical, it's a very similar composition. Okay, next slide. So after the inter-array cable leaves the string of the wind turbine generator, it enters the offshore substation platform to another set of switchgear. And the job of the station is to take the inter-array voltage, which we said before is 33 or 66 kilovolts, and transform that into the export cable voltage, which is typically between 120 and 400. Okay, next slide, please, Lou. Yeah, so after it leaves, the export cable then leaves the substation, and then comes into a horizontally drilled duct, which is onshore, into the transition joint bay, and then from the onshore export cable to the onshore substation, ready for conditioning. for the grid. Okay, next slide, please, Lou. Okay, so we see the typical layout of an offshore wind farm. So we now consider the transportation and installation aspects. So you can see there's the 3 wind turbine jackets sitting on top of this dumb barge being towed by 2 tugs. So the jackets are sea fastened, so welded and lashed to the barge. And then when the appropriate weather window opens, they commence transfer to the field ready for installation. It's important to note that, with major operations like this, the transportation installation aspects, there's a requirement for the marine warranty surveyor to issue a certificate of approval for this activity. We'll maybe talk about that later on. Okay, next slide, please, Lou. Okay, now we can look at some of the offshore construction vessels for installation of the actual wind turbine. Given the size of the equipment to be installed, the vessel needs to be pretty big and have the capacity for safely transporting and installing the assets. So if you look at the picture on the left, this is a heavy lift crane barge, and if Lou can maybe hover over the legs, this is a jack-up barge with 4 legs. It jacks itself out of the water to maintain stability, so it's easier to install. And again, in the case of a monopile, in this case, a certificate of approval is needed for this operation. The image on the right is just a jacket just in preparation for loading onto the barge. Just if you look at these things are pretty massive. Okay, next slide. Okay, now I'm going to sort of talk about some of the equipment on board the actual vessel. So the images on the left, this is the hydraulic hammer. It sits on the deck. This is used to hammer in this case, a monopile. Next, please, Luke. So you've got the monopile there. It's being upended with the underpinning tool from sort of left to right in preparation. Next slide, please, Lou. Slung overboard, and then located in the pile gripper. So this helps secure the pile prior to the hydraulic hammer being used. Okay, next. Okay, there's your hydraulic hammer and your compensator coming off the deck. Just going to, again, one of the cranes on board slings this over and then pushes, hammers the monopile into the seabed. Also, the weight of the monopile itself has a factor in helping secure it to the seabed. Next, please, Luke. Okay, so we're just taking a brief look at the installation and the monopile, and I just look at some of the component parts. You can see the image on the left is the jack-up barge. That's the blade rack. I think Luke can hover over there. That's where the blades are stored. These, if you don't mind, Luke, hovering over the jack-up legs. This is a bit of a clearer picture where you can jack the barge up out of the water. The image in the middle is the nacelle just in preparation for loading, and the last one is just it's on its way. Okay, so far left, that's the mast. Again, this after you install the foundation and transition piece, you install the cabling, and then you go back and install the mast and the nacelle and the turbine blades. So this is just a quick summary of some of the quick picture of some of the components. Okay, and so the image that's the fully installed wind turbine generator on the left. Easy to recognize. The picture in the middle is the vessel crane with the spreader bar. So this is used to distribute the weight when you're picking up the blades from the blade rack. Okay. Again, this is after you've installed the foundation, the transition piece, the cabling, and the mast. You have to put the nacelle on top before you can install the wind turbine blades themselves. Okay. Again, very briefly, this is just, again, the spreader bar, picking up the blades from the rack and lifting them for fastening to the nacelle. Okay. Okay, so taking a step back before the installation of the mast and the nacelle and the blades, the cable is installed. So you do the monopile, or you do the foundation and the transition piece first. So the cable lay vessel in the top left is very important installation asset. Typically, these are dynamically positioned vessels. So they've got azimuth thrusters located on the hull bottom, which can rotate 365 degrees or 60 degrees to maintain sort of position when they're installing. The cable, either the inter-array cable or the export cable, is spooled onto the vessel carousel. So that's the long, you can see it like it's this cylindrical bucket. It's under controlled tension over this yellow quadrant. This takes quite a long time. You've got to, depending on the length of the cable you're doing, it could take maybe like 2 weeks. It's a real laborious process because the integrity of the cable has got to be maintained. We don't have time to go into the installation method for the cabling, but I think maybe if at request we can do it in any future presentations. Next slide, please, Lloyd. Yeah, so some of the other vessels involved, this is a dive support vessel on the left. This would have an ROV on board, which is the picture on the right. So the ROV and the dive support vessel are used during the cable installation and also in the cable pull through. When you're pulling the cable from the trench into the J tube of the monopile foundation and or whatever foundation you have, up until the switchgear in the wind turbine generator. That's a very high-level summary. Lou's going to take over now and discuss some case studies, and then we're going to, as Nigel said, come together at the end for a Q&A. So over to you, Lou.
Thank you, Nigel. I think, sorry, it's Neil. Neil has taken us through some of the basic of the wind farm and also the components, how they are put together in the offshore environment. For next session, we are going to marry some of these processes and the kind of losses that we can see. So we begin with the first phase, which is the after fabrication of the components, they get shipped to the location. If you recall, Neil has previously showed us the lifting of these jackets on which the wind turbine are supposed to sit onto the barge. This particular case study is in the Alpha Ventus offshore wind farm, which is located in Germany, North Sea, 45 kilometers north of island of Bochum, west of Hamburg, and it's basically one of the first offshore wind projects in Germany. It produces about 60 megawatts of power, consisting of 12 jackets in a 4x3 array configuration. So what you can see on the screen is these 3 jackets, which is similar to what Neil has showed previously, being loaded onto the barge. From the first look of it, one would be rather uncomfortable because of the structures being so high, and therefore it is natural to feel concerned that with this kind of center of gravity, that it may not be that stable. However, considering the cost that comes with shipping these structures from point A to point B, clever engineers would have to do the engineering calculation, work with the risk surveyors, the MWS, which is the marine warranty surveys, to secure these jackets onto the barge. Now, for this loss, what happened was the jackets were secured onto the barge together with the lifting gear. And this lifting gear somehow became loose during the voyage. And what happened is it was begin rubbing against the structural members. You can see from the center pictures on this cross bracing that they have scuff marks. And these scuff marks would actually affect the integrity, the paint integrity, the coating integrity of these steel members, and they have to be addressed. So readings of dry film thickness of the coating was taken, and app sailors were sent on site to rectify and repair the bracing. This is not a very big claim. It's about 100,000 in quantum. However, it does bring us into the perspective of how effective or how comprehensive or what kind of involvement that we want from the MWS surveyor. Because from going back to the slides, loading, unloading of these structures, and doing the critical heavy lift, the surveyors will be there, but it is unlikely surveyors will follow the voyage, and these are the kind of potential gaps that one would need to consider when it comes to managing the risks during the voyages. The next example deals with the installation of the jacket itself. This is in the Galloper wind farm, which is in east of Suffolk, UK. It's located in shallow waters, and this is about a mid-sized wind farm with 250 megawatt capacity, 56 units. And for these jackets to be secured to the seabed, piles, which is almost as high as the jacket itself, go through at the base of these jacket, the pipe sleeve, somewhat like a nail. And the profile of these piles at this end, where it enters these pipe sleeve, are that of as sharp as the sharpened profile of a nail. So, depending on the tolerance of the grout seals, and also the profile during fabrication, which sometimes due to workmanship they can go out of dimension, then during the entry and the piling operation, these grout seals can get damaged. And because the seals itself is to hold the seal nice and tight so that it can keep the jacket secured to the seabed. If these seals are not there, then you risk, number one, moisture going into the between the interface, and also these piles will not be able to securely secure the jacket to the seabed. So for this particular claim, it is about $4.5 million. Ultimately, when for piling operations, if things go wrong and you already started piling and the piles have gone through a distance into the depth of the seabed, trying to take them out is a very big challenge. You involve a lot of underwater work, and sometimes even with underwater jacking. But for this particular case, they were able to install a silver plug underwater and able to resolve the issue. Closer to home in Asia, we have a case which is, I would say, a form of a typical marine peril. The transition piece, which is in yellow in color and is colored yellow to keep mariners alert that there is a object or structure at sea. So in this particular instance, the marine vessel that's working in the field were unable to control the vessel, and it went into and make contact with the transition piece. So for those who are experienced with marine claims and have actually operated vessels or watercraft before, keeping a watercraft under control when it is in motion is very difficult. It's not like driving a car where you can slam on the brakes and then you have you can put a car to a stop. So when you're in motion and in the sea, the only thing you can do is to go in reverse propulsion, or you just dump the anchors down. And in this particular instance, when they dump the anchor down, they actually snag some of the subsea cables. So it is not only the contact with the transition piece, which is a cosmetic damage, but it also caused damage to the cables itself, which is more expensive bit. So for this, the entire length of the array cable was replaced. This is a picture that shows that the center picture, especially the subsea cable being disturbed, and this length here is actually the amount of displacement. And if you go down, and when this is amplified in the waters, it will be a considerable length, at least a few folds. This is another example of cable damage which occurred due to during installation. For this, it's like the cable was paid out. If you recall what Neil has said, that for cables, when they are installed onto the carousel, they took a lot of effort to reel them in, and when you pay them out, it has to be done in a appropriate sequence. Failing which, if you pay over, there's too much slack, and we lay them on the seabed, you get bendings like this, or loops like this, looping like this on the seabed. And this cause issues. First thing is, the cables during installation, they have manufacturers' guidelines that they're not supposed to exceed a certain bend radius. If they do, that actually affects its working life and also the potential warranty issues. However, another issue when it comes to loops like this is understanding how these cables are actually made. Neil has shown you pictures, a cross-section of a 3-core conductor cable. The cables itself are very much similar to the wires that we have back in our house. People who are handymen at home and have actually spliced some of these cables, they are not they're seldom a single copper cable. They consist of many strands of finer cables. Likewise, for these cables, they are made exactly the same way. They consist of many smaller diameter cables. They are being braided, and then for 3-core cable, is 3 braided copper cables rolled into one. So when you lay them in an appropriate way, these braiding will undo itself, and therefore you have this phenomenon called bird caging, and this is itself is damage. This is another example that we have. This is in the Greater Gabbard, which is a larger offshore wind farm in the UK. But this particular one, this occurred when the cable was being laid onto the seabed. So for these cables, sometimes they need to be buried especially for the static cable. So these are paid through, extruded through a plow. The plow itself is a equipment or tool that actually cuts into the seabed so that it allows the cable to be when it's laid, to be buried maybe under 1 to 3 meters of into the seabed. So they are supposed to be in sync during the cable lay. Failing which, you have issues where the plow itself may cut into the armor of the cable, leading to damage like this. The last example is this in an example in the North Sea. This relates to a export cable, and for the export cable, it is similar, except that for export cable, normally they consist of a single core copper conductor. And when you talk about single core, this means that the conductor is thicker, is heavier, and therefore more expensive. So this is a case where during deployment that there was improper lifting, and during installation, the cable exceeded the bend radius and had to be replaced. So I've covered a few case studies on the kind of losses that we expect on the offshore environment, and many of you will realize that I haven't begun talking about losses that's related to the blade or the nacelle itself, or even the installation of the top piece, the tower piece. And this is because these are the kind of losses that are common in the traditional energy market. However, let us go through some of the challenges that we see in this offshore construction environment. The first, lifting. So as many of the wind technology it gets better, it also means that they're going to go bigger, larger, and they're going to deeper waters. So for first and foremost, for heavy lift, one of the issues is the lifting tool. And for what we can understand is some of the heavy lift cranes in the world is about 10,000, 15,000 capacity, and they are very, very, there are not many vessels that are able to have that kind of capacity available. So as more and more of these projects come on board, there will be a scarcity for these vessels. Transportation, this is both onshore and offshore. When the blades get to a certain length, you have issues with deploying the kind of vessels that are able to handle the length and the weight. For installation, again, these relates to us going into deeper waters. Where we are nearer to shore, I think there are more resources and there are better support for us to do the installation work. In deep waters, so going to deeper waters, I think one of the issues is the traditional fixed structures will not be able to go. There's a limit to how long we can build the jacket and how far we are and how far we can do with this technology for the fixed structures. So when we go into deeper waters, the next technology we'll be using will be the floating structures, and that itself will form about 2% of the world energy come 2015 will come from offshore floating wind technologies sources. Vessels itself, this is again an issue of scarcity. The kind of special vessels, lift boats that's needed to install these wind farms are limited. They are always committed to a project. So when things go wrong, it is very difficult to find a vessel that is free. It is very much like a taxi driver. For a taxi driver, they always want to be hired and be on the move. So they will not be waiting for an accident to happen and going to that site to address or resolve emergency issues. And if they do, they're going to charge the sky for it. Labor-wise, I think on the engineering front, there is not much of an issue. However, when it comes to things like the execution of work in the offshore environment, then I think that is very much lacking, and the number of service providers in this space is also very limited. Materials itself, that's another issue, because what we are seeing is, a lot of these, some of these wind farms, if they are of, they're mass produced and of similar kind, similar build, similar manufacturer, is not so much of an issue. However, if you're talking about, going into bespoke technology like floating wind farms, and these are not really tested in the market right now, these would be very expensive. Investment, yes. So for investment, a lot of the new technologies, these are actually funded by the government. The cost of offshore wind farm actually is coming down. I think in another 10 years' time, it will become even more feasible. We have more and more of these projects offshore. Climate change is a challenge because that actually make it less predictable in terms of how much we can generate power from offshore wind. And also, it also makes the works offshore for installation and production a little bit more challenging. The last but not least is on the end of use disposal. So wind technology has been there for at least 10, some 15 years right now. And most of these have a design life of 20 years. So right now, for looking on the onshore wind turbines, we have seen in some parts of US where the wind turbine are decommissioned, and these wind turbines, onshore wind turbines, the blades are being are being stored in landfills right now. So there is a company that actually do the stripping of and recycling of these turbine blades. However, when we look into some of these works offshore, then we have to consider the kind of how are we going to close the loop when it comes to the final decommissioning and disposal of wind turbine generators. So I think I've come to the end of my session today. I'd like to invite Nigel and Neil back for the question and answer session. Nigel? Neil?
Yep. Yeah, sure, Lou. Yep.
Thank you, Liu, Nigel, and Neil for that. We have a lot of interesting questions in the chat. So the first one would be, does Sedgwick have experience in managing claims for offshore fishing farm platforms?
Sorry, offshore
Fishing farm platform.
fish farm platforms. For us in Asia, I can speak for Singapore, and we do have a lot of fish farms around Singapore. We don't really get a lot of work like that, but at the end of the day, it's just another marine claim. It's just a different subject matter. I'm pretty sure within our network, we do have specialists in agriculture, because it generally comes under the farming category, I guess, rather than sort of the marine construction that we would look at generally.
Thank you, Nigel. For the second question, what is the average quantum for wind losses, and what is the cost trending towards? That is a deep or gentle trajectory.
It varies, and we've seen this as well. Very similar in the oil and gas side of the marine construction. There was a time when vessel rates they went through the roof. Some of the vessels, specialist vessels, heavy lift ships, you were looking at $500,000 US a day to hire them. As an example, on one of our slides there, we showed the Bull Tern, which is a Fred Olsen vessel. That's a pretty specialist vessel. It can jack itself out of the water up to 70 meters. It's got a crane that can lift 1,500 tons to a height of 158 meters above its deck. That vessel is $300,000 US a day. Cable lay vessels, $150,000 a day. And as Lou mentioned, it's all about supply and demand. And what you'll see is, as more and more of these offshore wind farms go in, if more bespoke vessels are not being built, then the price will increase significantly. And even the mobilization times. If you, for example, if a cable lay vessel is in the field doing your inter-array cables and it finishes the project and you find a damaged cable when you're doing the inspections, it may have another job to go to. So it's not going to hang around for your repair. So you may have to bring it back to do the repair. and I've seen mobilization charges $7 to $10 million US just to get the vessel back there. So, to answer the question, the repairs are extremely expensive when they go wrong. If you catch them early enough, you can use contract vessels, hopefully at contract rates. But if you've got to bring in vessels to do a repair, it can get really expensive very quickly. And generally, supply and demand, and it's the vessel rates that drive the value of the claims, not so much the repair of the equipment itself, the components required. It's the marine spread that drives it.
Thank you, Nigel. And based on your insights, what do you think? Why are there more wind investments in Northeast Asia compared to the Southeast Asia?
I think I can take that question.
Mm-hmm.
Yeah, I think for a start, Northeast Asia, if you look at geography, Southeast Asia, you have on the west of the Philippines bodies of water that's under political contest, and therefore I think investment, if you go further into these bodies of water, that is a main cause of concern. Therefore, I think investors are reluctant to actually go into that space. And if you go into the other side, along the Straits of Malacca, that is actually a trading zone where a lot of vessels pass by. So I think again that would make offshore wind not so feasible. And that's also considering that along that zone near Indonesia, we are in the Pacific Ring of Fire, and that itself pose a challenge for the stability of and feasibility of these projects.
Thank you, Liu. And for the next questions, we have two parts. First, what kinds of work can one expect in the maintenance of the mast and subsea cables? And the second question is, how far in kilometers are the subsea cables from the foundation side to onshore power substation? Could you give an example, like a minimum and maximum distance that you have encountered before or you have seen before?
I guess it depends where the wind farm is, whether it's near shore or offshore. Generally, a lot of these things are sort of over the horizon. As Neil mentioned earlier on, it's I think to keep it away from spoiling the view, if you like. So it's out of sight. I've dealt with a claim with a subsea cable that was 135 kilometers long. But you can get down to 50, 30 kilometers, maybe a bit closer if it's in an area where there's not so much habitation, So it can vary. And obviously, the cost for the repair varies as well. The one I did, there was an issue. It was damaged during lay, and the contract basically didn't allow any field joints, so they couldn't cut the cable and splice in a new section. As per the contract, it wouldn't allow them to do that. So there was lots of heavy negotiation between insurers and the principal to come up with an effective repair that was that satisfied the principal and even though it was outside the contract terms. So there was as loss adjusters, we had a lot of work to do on that one. And sorry, the first part of the question was?
The first question is, what kinds of work can one expect in the maintenance of the mast and subsea cable?
Right. Again, for the mast, there would be a lot of inspections. If these things have got a design life, of sort of 20 years or so, it may be a case that as it reaches the end of its life, and we're not sure yet because this is a relatively new sort of technology. They may retrofit the mast with a larger generator, but there would be the normal inspections like non-destructive testing of welds, and inspection of foundations. You may have to send an ROV down as a remotely operated vehicle to film around the subsea structure, cables, resistance testing, and the like. And again, flying an ROV over the cable route to check that there's no scouring. That's where the currents in the area could take away the seabed from where the cable is buried and expose it, which it can result in damage that way. So it would be a lot of visual inspection and non-destructive testing during its service life, because they are static pieces of equipment, really. Once they are installed, in theory, they shouldn't be going anywhere.
And just to add on to what Nigel said, I think it's important to look at the human activities around these wind farms as well, because normally where there are wind farms and they have cables like that, they tend to attract fishers and the fishermen. So fishing activity and keeping these zones being a special excluded zone, that itself, it depends on how strong the government's will is to keep vessels away. Because if they are there, chances are, someone's going to snag the anchor or disturb the subsea cable.
Yeah.
Thank you. For the next question, as the technology matures, do you see a shift in type, quantum, and frequency of the claims?
Yeah, look, I think, we don't see a lot of major claims with the installation per se. And when I say the installation of the piles, the masts, the nacelle, the blades, etc. Heavy lift has been around for a long, long time. With the offshore, again, go back to the offshore oil and gas construction. So that side of it is fairly well developed. We see a lot of issues with cable lay, and the technology used to bury the cables once they're installed. Once the cables are paid out off the back of the cable lay vessel, as Lou said, we showed an example there of what they call SimOps. That's where the cable comes off the back of the vessel and it goes through a bell mouth in a plow, which is towed by the cable lay vessel, and it buries the cable sort of simultaneously. We've seen damage there. There's another type of cable burial where they use a remotely operated vehicle, and it blasts the seabed either side of the cable with high pressure water, and the water fluidizes the seabed, and the cable sinks under its own weight up to about 2 meters below the seabed. But that generally works in soft sand or sediment type seabeds. It won't work in rock. In rock, you've got to go back to trenching methods where they use like a subsea bulldozer to dig a trench. So we see a lot of damage with cables there. I'm not sure, and that goes back years. The technology hasn't really changed that much. The ROVs are more complex and they're getting bigger, but the technology itself is not really developing. It's quite well advanced as it is. I think it's the materials that are changing. Like for the blades, the composites, etc., are getting a lot more complex now. They're lighter, they're stronger, but the techniques for construction have remained fairly constant for quite some time now.
Thank you, Nigel. Being conscious of the time, I think we'll just answer one more question. We are happy to reach out to you for those who still have questions. So for the last question would be, have there been any liability claims relating to offshore wind farms? Is there any damage to seabed and marine life with these wind farms?
That's quite an interesting question. We've certainly seen issues with bird life, migratory patterns of birds, if these things are placed in the wrong place. And I would suggest it's the same with marine life. And it depends where the farm is going to be built, I would suggest. Europe, UK, they definitely look at, as part of the consent process to allow the farm to be built, they definitely look at the impact on the environment, to sort of wildlife, etc. I'm not sure we have the same. It's as thorough in some other developing countries, because maybe the need for electricity outstrips the need to protect wildlife. So, I think it's something that will develop as time goes on, and there's more and more of these installations taking place. With the subsea foundations, if it's anything like an oil platform, for example, the structures tend to attract more wildlife than the sort of damage to the environment. You see a lot of fish species, sharks, etc., that they'll actually trawl around the platforms. So that hopefully it's a bit of an artificial reef. It might be a bit of a benefit there. Liability, yeah, we do see some during construction side of it. Someone does something wrong. Hopefully, if you've got a good marine warranty surveyor on board, you have a good program for the a good design, a good program for the construction, a good marine warranty surveyor. That should minimise the cost of any the sort of chance of any liability. To be honest with you.
Yes. So yeah, just to add on to what Nigel said, I think liability mostly will fall, during the construction phase, because once you completed the, especially this fixed structure wind turbines, they are like the lighthouse. They are immovable. So unless we are talking about them going into deeper water, floating structures, and then they lost their moorings, and then they're just like floating around, like becomes a floating hazard, then we talk about that kind of liability. But so far, I think once the construction is complete, I think liability in this form is very, very minimal.
And what I would say is, under say a well car policy, there's hold harmless clauses for generally, the principal, main contractor, subcontractors, etc. So that liability is generally waived in that instance. And if you go back and look at the marine warranty surveyors' terms and conditions, their limit on liability is extremely low. We have had issues with offshore construction whereby a contractor was changed last minute, or a contractor acquired the contractor that was named in the policy, but the policy didn't reflect the name change. But that was a legal issue. It was above our pay grade. Lawyers were engaged to try and get to the bottom of that and see whether there was any avenue for recovery. But generally, the hold harmless clauses are fairly watertight in offshore construction policies.
Thank you very much, Nigel, Neil, and Liu, for that very insightful talk and discussing the construction offshore wind farms, case studies on claims, and thoughts on risk management. We're delighted to have you as part of our program and truly appreciate your contributions as our speakers. And with that, we have come to the end of our presentation. Our educational program for 2024. I would like to take a moment to thank you all once again for the support, and it's truly a privilege engaging with such diverse and vibrant group of participants and resource persons from across the Asia Pacific, Middle East, and Africa regions. Your active involvement and enthusiastic participation have indeed made this program a success. We look forward to staying connected and continuing our learning journey together with Lloyd's Academy, and we truly hope that the skills and insights gained over the past months will serve as your foundation for future success and collaboration. Feel free to send us your feedback through the form that I will be showing shortly, and reach out to us or to our speakers should you have any more questions. This has been your host, Shai from Lloyd's Asia. It has been an honor bringing all these educational opportunities to you. Thank you all and enjoy the rest of your day. Bye.
Bye. Thank you.
Bye-bye. Bye.